Hey, welcome everybody into the NGK Tech Garage. Today we're talking air-fuel ratio sensors, or as James mentioned earlier in the chat, the voodoo sensors, because there's a lot of confusion and misdiagnoses or lack of being able to diagnose revolving around the wideband or air-fuel ratio or linear or UEGO or whatever the name of the sensor happens to be called on that specific vehicle. So the biggest thing with these sensors is they look so much like a standard action sensor. Here, standard action sensor, right? Threads into the exhaust, plugs in, 4 wires on here, a little bit of anti-seize on the threads. I mean, pretty standard. We've been replacing those for years. We get into some of the wideband sensors, and here is a 4-wire wideband sensor, okay? Looks very similar, 4 wires in the connector, still threads into the exhaust, still has a little anti-seize on it. You thread that thing in, and you're good to go. Little bit of confusion with the 4-wire sensor. Now we're not going to cover the 4-wire sensor today because we're going to be talking mostly on domestic vehicles today, and most of the domestics are going to use this pumping circuit style sensor. This sensor here has 5 or 6 wires, a little bit different looking, so if you pop the hood and you see one of these, you definitely know you're looking at a different style sensor than a standard action sensor. So we have more wires going to our connector, a little bit different. But the similarities in looks and installation is really where the similarities end. These sensors are incredibly different in both operation and function for the vehicle's computer. So the biggest benefit with a wideband sensor is the fact that it monitors a wider range, okay? We're able to see more than a standard O2 sensor can. A standard O2 sensor really can only read stoichiometric, right? That 14.7 to 1, and anything above that is lean, anything below that is a rich condition, right? It doesn't know how rich or how lean though. We bring in a wideband or an air-fuel ratio or UEGO or linear or whatever it's called, because each vehicle manufacturer tends to call it its own thing, but we bring that sensor in, and now we can read air-fuel ratio down to rich at like 9 to 1, maybe even lower, and lean all the way up into the 20s to 1, and some sensors can range even further than that. So we have a much wider range, but the biggest thing is not only the wider range, but we're able to control fuel in real time, in closed loop, and we're able to see exactly how rich or how lean a certain condition is. And it really gets rid of the ratcheting effect that we've seen with short-term and long-term fuel trims on vehicles. And now we're actually able to do a full system fuel control at wide open throttle. So on our on the Autel tool here, I went out and test drove this 2014 Ford Fusion 2-liter turbo in there, and went out on a test drive, and you can see I have some data PIDs pulled up on the screen here, and you can see our engine load and our short-term fuel trims reacting, but the only PID that I have available for the action sensor does nothing. But the biggest thing here is, let's see if we can get it right at like the 99 point, or 91. Well, it was close. There we go. Oh, yeah. So 91% engine load, that's wide open throttle. But look at our fuel system status. We're still in closed loop, and that's a big deal, right? We're able to still control fuel in closed loop with a wideband sensor because it's able to do it fast enough, and it's able to read those enriched conditions of a wide open throttle event. But there is a little bit of cool information in here, and we'll get to this in a little bit, but where we go somewhere here, right here, we go to open loop. This is because we're in fuel cut, right? We were wide open throttle, we were pedal to the metal, high engine load, and then we suddenly went to no engine load. We were pedal to the metal and then we let off. Now the vehicle went off into fuel cut mode, and we still went into open loop because we went incredibly lean at that point. The engine was just an air pump at that point, okay? So there is still circumstances where we go into open loop, but generally speaking, a wideband sensor will be able to maintain that closed loop operation. So like I said, today we're talking about the 5 or 6 wire dual pumping or dual cell or pumping cell or whatever you might want to call that sensor and that style of operation. That's what we're going to focus on today because that's what we see most of the time on domestic vehicles. In next month's class, we're going to focus on either Euro or Asian vehicles, and those are going to use some more of the 4-wire wideband sensor that we're going to talk about during that class. So looking at this little diagram that I drew up, we have our PCM over here on the side, and then we have our sensor right here. Okay, we'll start up at the top. Battery positive is going to be fed in from usually from a fuse in the fuse box, and we're going to feed that thing power to our heater circuit. Now, just like most normal standard oxygen sensors at this point, we're going to be pulse width modulating that ground side control. So we're not just turning this thing on power and ground 100%. What's interesting here is this heater does require more temperature. So a wideband sensor takes about 1500 degrees of temperature for proper operation, okay? The unique thing about this is with a standard oxygen sensor on your vehicle, usually if the heater goes bad, yeah, you'll set a code, but the sensor will eventually become responsive if it's close enough, if it gets hot enough, okay? Because we're able to maintain that temperature, the exhaust gets hot enough to make a standard oxygen sensor create that reaction inside and create that voltage. A wideband sensor will not function without a operational heater circuit. So if we have a bad heater in the sensor, if we have a lack of power or a lack of pulse width modulated ground from the computer or any wiring issue in between, we're going to set a heater related code, and then the sensor will not function. It will never function. Even if you let this thing sit with the hood closed for 3 hours running, the sensor is not going to be able to get up to 1500 degrees in exhaust temp, okay? So let's jump down now from the heater down to the bottom side of the sensor, and this, for those of you that understand how a standard oxygen sensor works, is going to look a little bit familiar. This point right here, our measurement chamber, is where exhaust is going to be taken into this sensor. Then we have a reference air chamber, and we have this Nernst cell in here, and this is going to operate just like a standard O2 sensor. If there's a difference in air, in oxygen molecules across this cell, we're going to have a reaction across there, and we're going to create voltage either above or below 450 millivolts. If we're running a stoichiometric mixture inside of the measurement chamber, our Nernst cell is happy and we're doing 450 millivolts from the computer right here, okay? But if we're not at 450 millivolts, if for some reason we're running rich or lean inside of our chamber, on a wideband sensor, our PCM is smart enough to be able to maintain this 450 by using what's called a pumping cell. Okay, so we have a cell down here, just like a standard O2, and then what we're going to do is we are going to literally pump oxygen molecules in and out of the measurement chamber to make sure we keep this cell at 450 degrees. This current flow, because like any pump, it takes current, that current flow is what the PCM is going to use to infer the air-fuel ratio. Okay, so if we look at a operation of a sensor at 450 millivolts, we're going to say that this is a stoichiometric mixture, and all I did was create blue dots in here for oxygen molecules and just made them equivalent to reference air. That's not exactly accurate, but for today's class, just to understand that in a stoichiometric mixture, we are not transmitting or creating any voltage across here because we're not rich or lean. So we're going to stay at our 450 millivolts. Everybody's going to be happy, and our current flow is going to be at our 0 mark. I should have put a little 0 here, but we're going to have no current flow because our exhaust mixture is stoichiometric. But if we run into a lean condition being an excessive amount of oxygen in our exhaust, in our output of our cylinder, if we have too much oxygen, at that point what we need to do is we need to pump that oxygen out. That's going to take milliamps or even potentially microamps to make that happen. That's what the PCM is going to watch. So we're going to pump that oxygen out, and you can see our milliamps here change, and now we're able to maintain that perfect mixture inside of the reference chamber, the exhaust chamber, whatever you want to call it, on the actual sensor. And same thing with a rich condition. If we don't have enough oxygen in the exhaust, and notice when I said rich condition, not enough oxygen in the exhaust, a rich condition has nothing to do with fuel. It has nothing to do with anything other than exhaust, than oxygen. Because an oxygen sensor, air-fuel ratio sensor, all they're doing is measuring oxygen molecules. They're a comparative style sensor. So a rich condition has nothing to do with fuel. It is a lack of oxygen in the exhaust. If you can keep that straight and understand that a rich condition is lack of oxygen, it makes you diagnosing a rich condition easier because you're not necessarily looking for an overfueling condition. You're looking for something that's causing a lack of oxygen in the exhaust. So in a rich condition, the current pump is going to have to pump oxygen molecules into our chamber. And again, all we're trying to do here is maintain 450 millivolts, and our current our current's going to go the opposite direction. That 450 millivolts is pretty much on these vehicles a steady voltage. The computer is that fast. That pumping cell is that fast. It is able to do that quickly. And then we monitor that current flow plus or minus here, to determine whether we're rich or whether we're lean. And now the computer has the ability to say, okay, X amount of current flow must equal Y for air-fuel ratio. Okay, that's going to be some sort of calculated algorithm that's inside of the PCM that they don't really tell us. I mean, we could maybe infer using short-term fuel trims and that kind of thing, but basically we're going to take a current flow and relate that directly to an air-fuel ratio. So when we're talking failures on wideband sensors, they're really going to be the same as your standard O2 sensor for the most part. There's more wires, so there's more potential for circuit failure. The heater circuit has to function, but really slow responding sensors could be due to age or contamination, you know, coolant contamination, oil contamination, silicone contamination. Any of those things that could affect a standard oxygen sensor really can affect a wideband sensor. And now a wideband sensor is so much more accurate and sensitive that those things that maybe didn't affect that oxygen sensor as much could affect a wideband sensor a lot faster or a lot more intensely. Circuit failures, of course, we have opens, shorts, and resistance. Again, we're running a super sensitive sensor here. Any sort of resistance could create issues. You know, if you take out the old test light and jam it into the connector, right, for checking something, you're spreading out those terminals. You could be inducing or introducing a resistance failure, an intermittent problem potentially. So you want to be careful that you're not causing problems when you're doing this testing. Of course, heater circuit failures, no heater, no operation. And then physical damage of the sensor. These sensors, of course, are under the vehicle usually. A lot of the widebands, for the most part, widebands are only the sensor one, the pre-cat. So generally they're in the engine compartment, but if they're not, they could be damaged by, you know, driving over something, or if something as simple as changing out a muffler or something and somebody's banging on the exhaust, that vibration or that rattle, maybe worn engine mounts, that could crack the ceramic that's inside of the sensor and cause the sensor to fail. So physical damage is also another big one that we need to look at. All right, so we're going to start today by looking at the, of course, domestics. We're going to look at Ford, Lincoln, Mercury, because they offer us a ton of information out on their OBD2 theory and operation through Motorcraft service. They offer a ton of information on how their stuff works, and we can relate a lot of that then to other vehicles. So we're going to start there, then we're going to do a little bit of GM, and then we're going to jump to Chrysler at the end. So Ford started using what they call the UEGO, or Universal Exhaust Gas Oxygen Sensor, in 2008. They call it that. It's a wideband sensor. They used it on the 3.5 liter V6 engine, the non-turbo 3.5 that we saw in like the, I think it was like the Taurus X, maybe even the Taurus in 2008. They're going to use two different sensors, an NTK sensor or a Bosch sensor. Now the only reason why I bring this up is because the testing that we're going to perform on these sensors and the values that we're going to expect to see once we get over to the vehicle will vary depending on what style sensor and what programming is built into the computer. Our heater temp on this sensor should be about 1472 degrees. We'll call it 1500. What's interesting is that just under 600 degrees, the vehicle has the ability to enter into closed loop. Now it can still set a heater circuit code or a heater code or a heater efficiency code if we don't get up to that 1500 degrees, but we do have the ability to get into closed loop before that sensor is up to full temp. And again, pulse width modulation on our heater they do not give it 100% positive power and ground because it can burn up the heater. Big thing with Fords, and really just about every vehicle today, is keep alive memory. You need to make sure you're clearing these stored values inside of the computer after you replace the sensor, because a lot of our vehicles today are smart enough to understand what that sensor did. Did it wear a little bit? Was the impedance different? Is there something different? We're going to get into sensor trim resistors. Those are going to vary sensor to sensor. You need to make sure you're resetting your keep alive memory after a repair, or you could potentially be creating a code or something with a brand new sensor. A fully operational 100% perfect sensor could still code if you don't clear out those variables. I thought this was a really interesting line in the information, so I quoted it. The air-fuel ratio, or excuse me, the air-to-fuel ratio is actually the output from the current controller in the PCM and not a signal that comes directly from the sensor. Okay, interesting, right? They're basically telling us that the PCM, the brain box, the magic thing that has the magic smoke inside of it that we're not allowed to see inside of because it's all proprietary engineering information, we're not able to see the direct air-fuel ratio that this engine is doing, that this sensor is outputting. It bothers me a little bit, right? Because we want to be able to test the sensor. Is there a way to do it? Is there not? Do we just trust the code? If it sets a code, you throw a part at it? I mean, we have to have a way to test, and we're going to do some testing in just a little bit, going from the most basic of tools with a test light and a voltmeter or DVOM, because we're going to do a resistance check as well, and then all the way up to full function scan tools, and I also have the scope hooked up as well. So we're going to kind of approach this from two different avenues depending on what testing equipment you have. We'll show them both at the same time. But there is ways to look at this sensor and look at what it's doing and have an idea, but we can't correlate that idea that we're able to form off of whatever we're testing to an exact air-fuel ratio. That is happening inside of the chip, that's inside of the PCM, and that's information according to the scan tool that we don't even get. Because if we look at the Autel tool again here, the information that I got was basically nil. I mean, O2 sensor, bank 1 sensor 1, which is our UEGO sensor, or HUEGO, but either way, as we scroll through, we're seeing tons of changes in fuel trims, in engine load, but we're stuck at 1.1 volts. So that PID is kind of useless, right? What does that offer us as somebody diagnosing this vehicle? It really gives us nothing. And I sorted through all of the PIDs on this thing. That is the only thing related to a bank 1 sensor 1, any sort of signal at all. So really driving this thing with a scan tool, yes, we can see fuel control, we can see short terms and long terms changing, we can see it going into open and closed loop like it's supposed to. This sensor is operating perfectly fine on this vehicle, but our scan tool, besides our fuel trims, is really not offering us any information of what the sensor is outputting, okay? So just keep that in mind when we're looking at these things. So here's a really cool diagram that is in that OBD2 theory in operation. This is a picture of the Bosch sensor. Now, everything that happens inside of this box is inside of the PCM, okay? We have our wiring here, a connector, and then our sensor right here. So we have our diffusion passage, the detection cavity, which is basically where the exhaust comes in, our pumping cell, our Nernst cell, and then reference air, okay? So that's all happening inside of the sensor, and then we start feeding that thing into the magic brain box, okay? But what we don't get to see is we don't get to see what exactly is happening inside of here, okay? What we really are concerned about is what it actually is going to look like to us. So IP and IA are both pumping current, okay? We're going to be pumping current in here, but again, we're very, very small amounts of current. I even hooked up the very sensitive Pico amp clamp on there, and I was unable to see any difference because there was so much noise basically happening on the circuit. What we're going to see is we're going to see a voltage output that's going to be very similar between IP and IA, and that voltage is going to have a small amount of current running on it that the PCM is watching. Okay, the PCM is watching IP and IA for that pumping current. IN and RE are our two Nernst cell connections, okay? Big thing to note here is the IN circuit is considered our ground circuit, but we're elevated at 2.5 volts above PCM ground. This is a big deal. We're bringing that up from normal PCM ground, which could be, what, a quarter volt, maybe 300 millivolts, something like that, on PCM ground normally, and we're going to elevate that another 2.5 volts above that. So that way we can really cut down on any sort of signal interference, because we're running such a hypersensitive sensor that is working in very, very little amounts of milliamps. We need to make sure that we don't run into interference issues. And when we look at the actual diagram coming up here for the vehicle, you'll see that we're running twisted pairs of wires, and that's also to help cut down on any sort of interference being induced from other circuits. Our Nernst cell voltage is going to output roughly about that 450 millivolts above the in, okay? So if we're above battery ground, you have to remember to factor that in. If you're hooking one side of your leads up to battery ground and you're testing at these, they're going to appear very different than if you hook one lead into RE and one lead into IN, okay? You have to remember that we're elevating the ground on this vehicle. Our heater current is about 0.5 amp to 3 amps on here. We're going to pulse width modulate that from the PCM, and we're going to feed that thing with power. Then we get the NTK sensor. Very similar looking, sensor design very similar. The connector's a little bit different. Our label resistor, trim resistor's in a little bit of a different place. You'll see we only have one pin for pumping current. We have a COM, a VS. Basically everything inside of here is, again, magic. This is kind of what we're looking for. Pumping current. Our ground on here is elevated even higher. We're at roughly 3.6 volts above PCM ground. 450 millivolts sitting above the inert cell. Current is about the same. This voltage input from the label resistor, this is coming from our trim resistor. This is a measured value, and we'll talk about that resistor in just a little bit. Heater ground, pulse width modulated again, and power on that, that heater. Generally speaking, you're going to find your wideband sensor heater and your narrowband, your bank 1 sensor 2 heater running off the same heater power, off the same fuse. So if you blow the fuse, you're going to have 2 oxygen sensor heater codes, right? That's just a quick check. All right, let's take a look and see the comments quick. All right. Just making sure I'm not missing anything super important. Can we get this PowerPoint? No, Chris, I don't give this out. You can watch the video as many times as you want, but I don't give out the PowerPoints. Takes a lot of time and effort to build these out. Okay, so let's get back to this. I want to just show you guys the, I don't want to call it a headache because I love diagnostics, but these sensors can set a ton of different codes. You know, maybe back in OBD1 days, you could memorize all the codes. Even in very early OBD2, you could memorize all the codes. Now, I can't. I don't know. Maybe there's certain people out in the chat right now that have all the codes memorized. But basically, what I want to say here is there are so many codes on this vehicle. You need to be looking up your code set criteria. You need to be looking up what it takes for that test to run to fail that code, because that's going to give you the information to proceed down that path. Because lack of switching sensor indicates lean bank 1. That's kind of a lot of information, right? It's saying our sensor's not doing what it's supposed to. It's indicating lean on bank 1. But what does it take to indicate lean? How long does that test have to run? Is it a single test? Is it a 2-fault test? Is it, you need to know all that information before you get into this. Basically, look up the code every time, because otherwise you could end up just, I don't know, chasing your tail. We can end up with these slow delayed response codes, which are kind of cool for different banks. The PCM is actually going to intrusively drive the air-fuel ratio to a stoichiometric mixture. It's going to do it intentionally, and it's going to expect this predictable output from the sensor. So the PCM is able to make sure that within X amount of time, I was able to return that sensor back to the stoichiometric mark. I'm not deteriorated. The sensor is not having any issues. It's doing what it needs to within X amount of time. But how long is that time? How can you replicate that test? You need to look up the code set criteria and find that out. So more codes, all related to sensor 1s, all related to wideband sensors, and still more codes, okay? And this is just for this 14 fusion, okay? So you have a ton of codes that point you down this avenue of diagnosis, right? You have this path to go, but you have to know what's on that path before you even get out any sort of tools. You know, what's the point of testing if you don't know what you're looking for? I just want to briefly talk a little bit about this air-fuel ratio imbalance thing that Ford does, and that I think most manufacturers are probably doing now, but Ford is nice enough to share the information. What we're doing is we're monitoring cylinder-to-cylinder air-fuel ratio. Now, Honda did this way back on one of their vehicles. They created this specially made exhaust header that they could predict, or they could assume which exhaust pulse was going past the sensor to determine which cylinder was which cylinder. Super cool. That's like, I don't know, 15-plus-year-old technology. This is doing it by watching the signal from the UEGO, from the wideband sensor. It's looking for hash. It's looking for noise on the scope, and that noise means that there's an air-fuel ratio imbalance between cylinders. So it's going to determine a normal hash, and then from normal, if it's dirtier, if the signal is dirtier to the PCM, that indicates that we have an issue. So again, if it's determining normal, that's most likely a learned condition. We need to make sure that we reset that keep alive memory anytime we change out the sensor. Take your scan tool, reset keep alive memory, okay? You could end up chasing your tail after you put a brand new sensor in that works perfectly fine. That still sets a code, okay? Super important. So the early air-fuel ratio imbalance could really just set a bank-to-bank air-fuel ratio imbalance. So it's similar to like a 171, 174 style code. But Ford took it a step further. They went with the AFITQ, which sounds really fancy, but basically it's an air-fuel ratio imbalance monitor that is going to be torque-based. Now that is a little bit confusing on what exactly they're saying. What they're doing is they're finding a way to look at very small changes cylinder to cylinder on our engine. So what they're going to do is they're going to watch the crankshaft position sensor. They're going to be able to figure out what cylinder is on its combustion event, what cylinder is now on its exhaust event, forcing that pulse down the exhaust, and it's able to watch that air fuel or that response from the wideband sensor. So what it's going to do, it's going to intrusively do this monitor. It's going to intrusively figure this out by running the vehicle intentionally, or excuse me, running that cylinder intentionally rich, intentionally lean, and once at stoichiometric. And it's going to determine this algorithm that it's going to call good, okay? Any deviation from that, and we're going to be able to set individual cylinder codes. So we first started seeing this on the 16 Explorer 3.5 and the 16 Taurus and Flex 3.5 and 3.7. Now personally, I don't have any experience dealing with any of these codes, but it's something super interesting and something that we need to watch for, because to me, I think this is an awesome diagnostic win for us, because now we could be, let's say that we have a misfire code and one of these imbalance codes. You know, maybe we're looking for an engine mechanical issue, or maybe let's say we haven't created a misfire yet, but we've slightly burned a valve, or we have, you know, rings that are failing, or we're running into all kinds of weird mechanical issues today on one cylinder. Burned valves are kind of common on some vehicles today. Maybe this air fuel ratio imbalance code can set before the misfire code. So now we're looking for something that is just very slightly tweaking the output of known good from that cylinder before we even set a misfire code, because as most of us who've worked on Fords in the past, we know how wide the range is for misfire detection, right? It was worse on older vehicles, it's better now, but still we know that the misfire to catch a misfire is a lot wider than what I'm thinking that this is going to be, because we're intentionally, intrusively running it rich, running it lean, running it at stoichiometric, and we're watching what that cylinder can do. Any deviation from that. I'm just thinking, you know, in the future here we're dealing with direct injection, right? Maybe an injector is partially plugged. Maybe it's not enough to set a misfire. It's not enough to change the crankshaft RPM quite yet, you know, to set that misfire. But maybe it's just enough to change that air fuel ratio, or maybe it's one of those EGR valves that we're going to start seeing on our vehicles, and maybe that has like the old ports like the Honda 3.5 had, right, where certain would plug up. Now you're feeding too much EGR into certain cylinders. Maybe it's not enough to set a misfire, but it'll most likely set this more sensitive air fuel ratio imbalance. So it's just something cool to look for in the future. Let's talk a little bit about heater diag, because it's important. If the heater doesn't work, the sensor doesn't work. We have this thing called the UEGO heater temp control monitor. Basically, the PCM is going to intrusively apply a very small amount of current, and it's going to measure the change in voltage. It's going to do what's called measured impedance. It's basically the effective resistance of the NERT cell across that 450 millivolt cell. It's going to be able to assume, it's going to be able to infer a temperature based upon the impedance of that cell. So as the cell's impedance goes down, our temperature must be higher. So the PCM is able to say, okay, we're at this level of impedance, we must be at this temperature. And that works pretty well, and that happened a lot pre-2012. We also had a separate current monitor. So we were able to watch the current, the PCM was able to watch that current and force it to run once per drive cycle, doing a true, let's look at the current test and sensor impedance, where basically the sensor was acting like it was a cold sensor, but the impedance was showing that it was hot. So it's going to force this test to run. But post-2012, a lot of the vehicles no longer have that. They're going to use that heater current as a reference or a inferred data using that temp control monitor. Basically, PCM is going to track the maximum amount of time that the pulse width modulation is at its max. It's going to set a time frame. That sensor should run max pulse width modulation for blank amount of seconds, and then we can infer that the temperature is here. We're going to measure the impedance of that NERT cell. If it's within range, great. If not, we're going to set a code. So we're going to watch that pulse width modulation. We're not going to measure the current on the circuit anymore. We're going to watch pulse width modulation and inferred impedance or excuse me, the impedance of the sensor to infer temperature. So there's no temperature sensor or anything like that built into these. We're using resistance across a cell to determine the temperature of the sensor. Okay, I said we were going to talk about trim resistors. We're going to go over it very briefly because really we're not going to have to worry about trim resistors too much because they're built into the connector. As long as the connector is okay, generally the trim resistor is okay, but you should know how they work. The NTK sensor's trim resistor is going to use a pumping circuit signal value, or excuse me, it's going to use an algorithm to correct the pumping circuit signal value. Because we had only one line coming from the pumping circuit, we're going to create this algorithm inside of the PCM. Our resistance value across that resistor is generally 3,500 to 1 million ohms. And we're going to command the module to read the value of RL. And RL is going to be used to achieve this compensation coefficient. So if we go back here, RL is going to be our voltage input from the label resistor, okay? So this is going to vary vehicle to vehicle depending on the size of the resistor they put in there. And they put the resistor in there to account for manufacturing differences. There's no such thing as two of the exact same thing coming off of a manufacturing line. So, being that this is so hypersensitive, our wiggle room in manufacturing is much smaller, so we put a trim resistor in so that way every single sensor's output to the computer will be figured out to be the same. But that trim resistor value is going to change, and that's why we see multiple samples are going to be used to determine this compensation coefficient, okay? Again, we're taking samples and we're determining a learned value, okay? It's going to classify this trim resistor into basically a rank. We're going to get codes if it's wrong, and if it sets a code, it's going to go to a previously stored rank. Now, this is a lot of stuff that we probably aren't going to ever see or have to deal with, potentially talking, you know, the rank and everything. But what you need to know is we have a trim resistor in sensor A. We figured out that this sensor failed. Maybe the heater went open or the sensor was just damaged, whatever. Now we put in brand new sensor B, okay? But we don't reset the keep alive memory. We're now in rank whatever, and it's possible that we could code because this sensor is a different resistance value, okay? That's going to change our pumping current, which the computer has learned that value for through that whatever compensation coefficient. It's going to change that, so we need to make sure we reset the computer back to the way it came, right? Reset the keep alive memory, let it learn multiple samples to determine the new sensors installed. The Bosch sensor is completely different. It's going to run that trim resistor in parallel to the pumping circuit. So we saw IP and IA both running to the PCM. PCM monitoring pumping current on both. We're going to be about 30 to 300 ohms on there. The IP is the true current coming from the cell, and the IA is the adjusted current. So the PCM is going to watch adjusted current, and that is going to be its value. So in summary, with Ford, you have to know which type of sensor you're diagnosing, NTK or Bosch. But really, you just have to know that there's two different sensors and these are the values that they output, right? Because I'm not going to be one that's going to have to do I don't like doing extra work. So if I start probing and testing that sensor and it's testing out like this or like this, that must determine it's this sensor or this sensor. But if it's anything else, I have skewed readings and I'm probably going to have to look a little bit further. But you can determine that off of like the resistor, the ground level, you know, it was I think 2 point something and 3.6 volts depending on the different sensor. So you can use some of those known goods to determine what exactly sensor it is that you're testing. I can read the code set criteria, it's huge. Code doesn't necessarily mean that the sensor's faulty, okay? So we could be skewing the sensor potentially. We're looking at half to 3 amps on the heater, and resetting that keep alive memory is key. And then again, just that quote at the bottom that the air-fuel ratio is inferred. It's calculated inside of the computer. Okay, so before we get to GM, I think we go and do some testing on this Fusion because it's been 35 minutes. That's a lot of talking. Terry, I am cramming a lot in today. I have a lot more to do, and that's why I've split this up by domestic, European, and Asian, is because it's just so much to talk about that I just wanted to make sure that I can get it all in and give you guys the best possible information to look at. So, whew. $20 for the PowerPoint. I'm not selling it, man. It's not for sale. All right, I don't know that I missed anything. So we're gonna go over and we're gonna start playing. So like I said in the beginning, I understand not everybody has an Autel scan tool or a Veris scan tool. They might just have a code reader. Not everybody has a scope or a picoscope or amp clamps or any of that. So what we're gonna do today is we're gonna do a little bit of testing with the multimeter, because I mean this is a really nice multimeter, but you can get multimeters for relatively inexpensive and a standard incandescent test light, okay? Very small amount of money spent to be able to diagnose this. I mean, these sensors can run from, I don't know, what, $7,500 all the way up to $250, depending on the vehicle. So big changes in price. You want to make sure you diagnose this thing right. You don't want to have to you know, eat that cost or whatever with that. So let's try not to mess anything up as I move the laptop over here and hopefully not trip on my face and fall on my face and not unplug the computer. And there's a lot of variables when you're playing with this stuff live that somebody said break a leg to me this morning. It's like, don't say that, I gotta move around the shop a little bit here and I'll end up tripping and falling on my face. All right, so we'll get the scope hooked up. I do have the scan tool hooked up so we can watch some live data on fuel trims. We'll get this guy all set up here. Let's take kind of a long window. We're gonna go 1 second per division here. We're gonna take kind of a long look at this. We'll grab, now 20 volts per division. We'll just start doing some probing of this thing. Now, on here, I actually broke out the connector here because it's kind of a pain to get to. So I've put in some other leads in here, just basically breaking out the connector so I can access it easier because it's just hard to get to, and I don't want to run into connection issues. So let's start by getting this guy out. And I think what I'm going to do here is I'm going to take something. Maybe I'll hold this up for you guys. We'll see. But we'll just test this in multiple ways. So we'll go voltage here. And we'll start by putting our ground lead. Ground lead is going to go onto battery ground. And we'll start by taking a look at, well, the first easiest check is we're looking for battery positive. I should bring up a wiring diagram so you guys can take a look. All right, so here's the diagram. Pin 4, green wire, being spliced, feeding multiple things. We're going to look at battery positive here, pulse with modulated ground on the ground side of the heater circuit, UO2, S11, and GREF. This is going to be our NERT cell across 2 and 6. 1 and 5 are going to be our pumping current and pumping current trim. So already just looking at the diagram, we have 2 pumping currents going in. This is probably the Bosch sensor. And like I talked about earlier, where I said that we're really trying to cut down on any sort of signal interference because we're so sensitive on the sensor, you can see in our diagram here, this little symbol right here, that thing right there, that means our wires are a twisted pair. They're twisted around each other, kind of like an ABS harness that we showed in a past video. They're just twisted to cut down on any sort of anything else being induced upon that sensor. All right, so we'll hook the scope up, and we're just going to piggyback the scope and the multimeter. And I think what we'll do is we will go some live data on the scan tool, and we'll grab, we'll get the vehicle running. So we're going to run in with this guy, get this all hooked up. We'll go diagnosis. Should have the key on. All right, keys on. All right, and what we're gonna do is we'll just grab some live data. We'll grab that 1 oxygen sensor paid. We'll grab short-term and long-term fuel trim. Oh yeah, come on. And this is where we introduce a time lapse and put some funky music over it. Do, do, do. Come on. I think it's just loading a lot of data PIDs. Okay. All right, so let's grab, oh, we don't really care about load at this point. I'm not too concerned. Downstream, these are both downstream sensor, but we don't really care about the downstream at this point. There's load. It's not under exhaust. We can go open closed loop, sure. Let's grab our fuel trims. Heated exhaust. Voltage. That's just heater on or off. Some other statuses. It's got a no fault status. That's kind of cool. We can see heater control. No fault. And then let's grab long term, and we'll just grab short term, and we'll call it a day. Oh, maybe. Come on. Okay, so let's just graph out short term, and we'll graph out this guy. All right. Let's go ahead and fire this thing up, and let's take a look at what we've got. All right, so I'm going to hook into the heater positive first, so we should see 12 volts. We should see 12 volts if I'm in the right one. Oh, going the right one. Okay, we have charging voltage on there. Looks good. Let's take a look at the ground side control. Oh, let me bring the scope back up. Take a look at ground side control. So that was pin 3. It's gonna be my green here. Now this is where using a meter gets a little bit different. You can see on the scope we're a battery voltage to ground type of pulse width modulated signal. On a meter we're seeing 8 point something volts, and that's because the meter is unable to refresh fast enough to give us the signal that we're looking for. So a meter falls a little bit short here, but we should see something other than 0 and battery voltage on this when we're using a meter. All right, let's go now to our pumping circuit. So pin 1 and pin 5. This is non-trim resistor. We're seeing a little bit of movement on here. I'm going to bring our voltage scale down on the scope. You can see a little bit of movement on there. And that's on non-trim, and on the multimeter too, you can see a little bit of movement. It's bouncing a little bit. So we can see a little bit of voltage change here, telling us that, hey, our sensor's kind of maybe doing something. And that's at like 2.2, 2.3 volts. Let's go on the other pin, pin 5. It's gonna be my yellow connector. And we're gonna see basically the same thing on pin 5. And then what do we have left? The nerd cell. So let's take a look at pin 6, which is going to be blue. And that is coming in at, what is that, 2.9, 2.975, so just under 3 volts on there. And then the other side, the ground side, again, we're elevating over PCM ground, so that's pin 2, that's going to be this one. and we're at 2.5. Okay? So again, we're at like what, 2.9, 2.5 for those two. So if I take my ground side off of the battery, take the ground side off the battery, I'm going to put this on the other side of the NERT cell, and we should see roughly 450 millivolts. And let me zoom in the scope a little bit. Do I not have a connection? Oh, I see. So we're actually negative because I have it hooked up the other way. Oh, right. Why does that not look right? Well, on the meter, we're seeing 0.448, so 450. I'm not sure why this isn't doing what it's supposed to. Okay, that's hooked up, that's hooked up. Did it freeze up? Oh, I'm just going the wrong direction here, my bad. I went to 200 volts instead of 200 millivolts. There we go, now the scope's doing what we're expecting. So we're at negative 450, and that's just because the scope leads are switched around. If we just switch them back the other way. So we take this one. That should give us what we're looking for. So 450 across the NERT cell. So we saw a little bit of the sensor doing something, right? It was kind of moving a little bit. It was kind of showing us a little bit on that pumping circuit. But what we can do is we can actually look at more fine-tuned on that pumping circuit. So what I'm going to do is I'm going to disconnect these so I know what I have in my hands. So positives and negatives. And what I'm going to do here is I'm going to hook the positive side of the leads, meter and scope, into, we'll go into pumping cell pin 1. That is my red connection. And we're going to take and we're going to go into the ground reference cell. So that was pin 2, our white wire. And what we're able to see now is if you zoom in really far with your scope, and again we're in negative voltage, it doesn't really matter, voltage above or below 0. But what we're able to see is the movement in our fuel correction. So we're at like 200, 300 millivolts here. Now, watch what happens if I disconnect the coil. So ignition coil down. Big change, right? All right, we plug that coil back in. And it's going to take a second for the computer to recognize, but we should see this number then come down. After the computer recognizes that the coil's plugged back in, it's going to run through a circuit test multiple times, make sure it's plugged in. And after a certain amount of seconds, it should, there we go, started working again, and immediately our sensor changes. That is how fast that's happening. And if we look at our scan tool, you can just see how quickly our field trims are changing. And actually, kind of cool, we were able to change our voltage dramatically on that sensor output. So we changed our field trims when we unplugged the coil, and we changed our voltage dramatically. So it's a cool little test that you can do. And again, we're between pins numbering, let's see, we're between the ground reference, pin 2, and pumping circuit, pin 1, okay? And we're able to kind of see what this sensor is doing. Now we can't directly correlate that off to a air-fuel ratio. That doesn't happen, right? Because that's an algorithm, that's something that's happening inside of the PCM. But we're able to look at that and have an idea that that sensor's working. We can force this engine rich, we can force this engine lean, and we can see that sensor respond accordingly when we're diagnosing these things. Let's jump over a little bit to heater circuit diag. All right, so changing gears a little bit here. Actually, the heater circuit diag on this one and heater circuit diag on that one will be about the same. That one's easier to get to, so I think we're going to focus on that one instead, just because I can access it easier. But really, I hope this is a good demonstration to show that yes, while a scope is awesome and it's really nice to have, we can get by performing some basic tests to have a relatively good idea of what that sensor is doing while using a meter. It's not going to be as fast, it's not going to be as accurate, it's not going to give us every detail of information we're looking for. It doesn't accurately display the pulse width modulation for the heater, but we can get a pretty good idea with a much more inexpensive, a much cheaper tool, really, is what it comes down to. A scope would probably be the right way to do it. A meter will get you by. So I think I'm going to bump back over to the other vehicle, and again, hopefully not drop anything or trip. And then we'll get into just briefly into GM, because it's going to operate, all these domestics really are going to operate very, very similar. But we're going to bump into that, and then we will get into this Chrysler. All right, so all right, let's see if there's any questions. Oops. Let's go here. Minnesota accent. All right. All right, cool. All right, then let's get into, I guess we'll cover just quickly into GM, because we don't have a GM car here, but they're going to be first using a wideband or air-fuel ratio sensor. You're going to first see it on the 1999 Cadillac Catera. That's that 3-liter V6 on that kind of interesting Cadillac. But that's where it was first used. Today, you're most likely going to see your air-fuel ratio sensors on a GM on the Cadillac models. The 2-liter turbo, the 3-liter in the Saturn, the Honda 3.5 that was put in like the Saturn View. It's going to be a Honda setup. That'll be a Honda style operation. And then the Pontiac Vibe, which is really like what, a Toyota Matrix, I believe it was. So Honda and Toyota, those date back into the 2000s on those for the Saturn and Pontiac. But really, even today, you know, like I don't know, the good old 5.3 coming off the line today still isn't using, or isn't shown to be using, a wideband sensor. So they're still doing traditional fuel control. There's probably, you know, a cost type of thing involved. Almost all these sensors are going to be the dual pumping cell type, except for your Vibe. That's going to be the Toyota style, and we'll get into that in the next class. Here's just a quick pinout of the wiring diagram of that Catera, and you're looking at similar voltages, similar setup. Pin 5 and pin 4 are going to be for our heater circuit, so we're battery positive, pulse width modulated ground. Pin 1 and pin 6 are most likely our pumping current, I believe is what we're looking at here. Yep, pin 1 and pin 6, if I could read. There we go. And then pins 2 and 3 are going to be varying voltage between 2 and 4 across that Nernst cell. Chevy Cobalt, very similar. 2-liter turbo in here. Very similar diagram, pulse width, modulated ground, power fed in. Looking at our pin 1 and pin 5 here is going to be our pumping current, because we have our resistor built into there. That's our resistor right there in the connector. And then pins 2 and 6 appear to be our across our Nernst cell on here. So it's going to be very similar testing. What it's really going to be is getting to understand what a known good looks like, you know, known good values, known good voltages, and then just figuring out what it's not. You know, is it a heater control issue? Is it a circuit control issue? Can you make it go rich? Can you make it go lean? Watch your fuel trims, that kind of thing. Then you get into like a 16 Envision 2-liter turbo, and the only spec I was able to find was heater current is somewhere between 0.3 of an amp up to 4 amps. I was unable to find any sort of voltage specs on here. But if you look at the diagrams between the Cobalt and the Envision, they're similar. I don't know if the voltage levels will be similar. Maybe they elevate the ground higher, could be. But we should really be seeing about the same thing. Nert cell is going to be an elevated ground and 450 on top of that. And then the pumping current will be a variable voltage, whatever they decide. But we should be able to see that move a little bit if we compare that against that elevated ground. Here's some codes that you're going to run into. We have the ability to see signal circuits, shorts, opens, shorts to voltage, and then also performance style codes. So there's a ton of codes that we're able to diagnose on these sensors. Here we look at a Cadillac CTS. I just put this in here because I thought it was a really interesting heater control voltage. So this is right out of service information, 4.6 to 5 volts on heater control, which is this guy right here. I thought that was just a very interesting voltage parameter, considering we're feeding battery positive into that thing. But again, the 2.6 to 3.1, 2.2 to 2.7, that's going to be our Nert cell, and then pumping current, we're looking at that voltage reading. So, I mean, there's a lot more that we could probably show on GM. I just don't have a GM vehicle here, so we're going to go into Chrysler now and show some things with that. So Chrysler really started using wideband sensors in 2003 on their diesel commercial vehicles, the Dodge Sprinter 2500 2.7 liter. I think that might have been like a Mercedes-Benz engine probably. In 07, they went into the gas commercial vehicles and a 3.5 liter Sprinter. And then in 2012, we really started seeing them in the first passenger vehicle, the Fiat 500 1.4, that's that multi-air turbo. That's actually what's in this vehicle right here, the 1.4. This is a 2013 Dart, but 1.4 liter, using the same sensor. And really today what you're looking for is the sensors are going to come up in the 1.4, the 2.4, the 6.2, and the Eco Diesel are really all they're using the wideband sensor in today. On the old school 6.7 diesel, I wanted to talk about this because they use an independent control module for the oxygen sensors. It's kind of interesting. It's basically a control module that controls these two sensors, these six wire sensors. They're identical to each other, front and rear, but we're going to run one before and after the oxidation catalyst. So basically, if you install this module, you do need to make sure that you reprogram it with the latest software, otherwise you could end up with DTCs. And this module does communicate with the ECM on a data bus line. So really what we're doing here is we're not necessarily doing direct fuel control, we're doing catalyst control. We're looking at that oxidation catalyst and making sure that it's functioning right, making sure that the after treatment system is working properly. It's going to compare the oxygen content, and it's going to run diagnostics and be able to set codes. I mean, really, it's no different than what we're dealing with. We just aren't going to be really looking at fuel control in terms of fuel trims. We're going to be looking at after treatment control. Diagram with both sensors. Going back to that module, it's laid out pretty well. You can determine what you're looking at here, and then we have our diagnostic, or basically our network line here, going back to the PCM. So again, both sensors are the same part number, and it's kind of unique that they are pre and post, but that's because we're trying to measure the difference across that catalyst. Most vehicles, like I said earlier, are wideband in the front, standard oxygen sensor in the rear. For now, that'll probably change as we go more with post catalyst fuel control, which is already happening but will continue to happen. What's kind of cool with this is they're the same part number. You could probably swap them front to rear if they come out nice. But we all know that you usually, at least up here, you have to get the torch out to take these things out. They get rusted in place. So you might not want to damage two sensors. And like with any sort of component that shares a similar living environment, if one sensor is skewed or deteriorated or running into issues, what is the likelihood that the other one is okay? You know, or the other one's maybe on its way out. You probably, it might be wise to take care of both sensors at the same time. All right, let's talk a little bit about this dart right here. This dart's kind of cool because it features these various tests, these cold start tests, it's got hot tests, and then it's got cold start at engine, or cold test at engine shutdown. So it's got a couple different ways to set codes and test this system, and they put it in this really nice / confusing chart to look at. But basically we're gonna start up the engine and we're gonna check the ASIC chip, or basically the control chip inside of the PCM. We're gonna make sure that that thing is okay. If not, we're gonna set an internal code. Great. Then we're going to do some cold start diag. Are we going to pass or are we going to fail? If we fail, we're going to set a generic 131, 132 code, and then we're going to go and do some sort of sensor cooldown at key off to do another cold circuit test, which jumps us into these codes. So basically what we're able to see here is we're able to take a sensor and test it one way. If it fails or if it passes, then we're able to follow up and perform more testing. So we can get a very generic code, and then we can also get a more specific code once it passes the other test. If you interrupt it mid-test, you'll be left with the generic. You won't get that pinpoint of a code that you could get, because you go from a 131 or 132 code, then you split that off into, well, I mean, we have what, 6 or 8 different codes in here, and really these are the codes that we will see on there, but it's going to depend on when the test is going to fail, or when it's going to take that test and pass or fail. So I just wanted to go over the steps that they call out in service information for diagnosing a generic 131 circuit low code. Step 1, as always, check your DTCs. Step 2 is check any correlating DTC first and repair that. So if there's something else that could be skewing the sensor, make sure you fix that first. Of course, they don't include check for TSBs or check for reflashes or any of that, which they should, but I guess that's they're just assuming we know that. Step 3 is we're going to unplug the connector for the sensor, and we're going to check to make sure that it's not shorted to any other circuit, which is okay, sure. Kind of, I don't know, continuity testing just sometimes leaves a little bit to be desired, but that's what they're saying to do. And if it passes that, if there's no issues with that being shorted to ground or shorted to another circuit, we're just going to, you know, plug that connector back in at the PCM apparently, and we're going to replace the sensor. That's step 4. I mean, kind of crazy. I don't quite agree with it. I think there's more testing that we can do, more things that we can make happen here. And then of course, step 5, if that new sensor didn't fix it, it must be an issue with, you know, broken wires, or, oh look, now we're going to look at service bulletins after we've already put in a sensor, and if there were no problems found, you're supposed to go out and replace the PCM. Craziness. This is why I'm not one to go out and follow these things verbatim. You know, we look for ways or little shortcuts maybe that we can take, maybe if they post us some known good values that we could look at, some ideas, but if we followed this verbatim, we could end up with an intermittent problem that ends up getting a sensor and a PCM and a upset customer because this check engine light's still on. So be careful following these types of things. Use them as a tool, don't follow them verbatim. All right, here's the diagram. Again, pretty standard. We're going to fuse in a 10 amp fuse feeding this guy. We're also going to feed the other oxygen sensor with it. So our heater is on a fused input. We are going to signal return and signal here are going to be our NERT cell. We're going to take positive current control. This is most likely some sort of pumping circuit. Heater circuit control, which is going to be our pulse width modulated ground. And then the trim resistor circuit on there as well. So let's get to playing with the Dodge Dart. So let's get the key on and we'll take a look. And we do have a little bit of information on this thing that we can look at with a scan tool. Grab a flashlight. So our sensor on here is actually located right here in the exhaust, just after the turbo. Kind of a nice location, pretty easy to get this sensor out, which is great. But then they run the connector down underneath the air inlet tube right next to a coolant hose where you guys probably can't even see it. I can see it down there, but it's right under here somewhere. Okay, that's where the connector is, which is, you know, really nice to get to and perform testing. But the sensor's easy to change. I guess that's cool. So I have the scan tool pulled up with related oxygen sensor PIDs that we're able to see on here. I got it in a custom data display already, so that's quick and easy. We'll get this thing fired up, make sure everything's out of the way. We'll take a look at what we can see with the scan tool. So right now we're still in open loop. And there we go into closed loop. And we can actually see pumping current in milliamps, which is kind of nice. And we can see feedback, but what I was unable to find on here, I was unable to find any sort of fuel trims in here. So if we look back through here, there was no fuel trims listed in this data. So kind of unfortunate, but we can look at feedback to determine rich and lean. And right now it's just cycling back and forth. We're able to look at our current, so that's really nice to be able to see on a scan tool. So let's start taking a look at our connections here. So we'll do basically the same thing. We're just going to run the leads together. So we're going to start on battery negative. And we'll start with, well, we know the sensor's working. I'm not even going to bother looking at the 14 volts. Take a look at our heater control. So pin 3. So if we get the scope up on the screen, oops. So there we go, we got our pulse width modulation. Our meter this time is reading 9.3 or 9-ish. So again, not accurate, but it tells us that it's doing something. And if we look at pin 2. This is going to be our positive current control. So we're at 3.5 volts roughly. That's what it's reading on here. 3.5. So that's our pumping circuit is going to hold about 3.5 volts. But if we do that same thing, where we now take our ground wire and hook into the low reference. So we're going to go into signal O2 return upstream pin 6. So all we're doing now is we're going here, we're hooking in the black lead, and here we're hooking in the positive lead. And we should see that changing of voltage again. That's not what I was looking for. Let's make sure we get into the right one. And there we go. So we'll get this guy all zoomed in. Get out of the way. So again, we're ending up with a varying voltage, and if we force this thing a little bit rich, you can see a direct response in the scan tool, on the lab scope, and on the multimeter. I'll bring this back over. But what's really interesting is where I'm spraying in this spray. I'm just doing a little bit. It takes a little bit for it to get to the exhaust. There's a little bit of time, but you can see everything changing. So we're able to look at a little bit of our output. Now, again, we can't correlate this directly to fuel trim or air-fuel ratio, but we're able to see movement or changes in our sensor. And then if we go pin 6, so we're going to just make sure that our nurse cell voltage is 450. We're going to go pin 6 and we're going to go pin 4. And that should be so somewhere here, there we go, there's our 450 millivolts. That's exactly what we're reading here. But what I'm going to do now is I'm going to show you guys how quickly this thing is able to respond. So a little bit of cleaner in there, and look, we did change a little bit on our scope. You know, right there, let me bring this up to 1 volt and I'll do it again. Let's pause this, let's throw a, oops. It's just, okay, so there we go. So we do see a slight change when we induce a little bit of fuel into here, right? Our nerd cell goes up just a hair, and then it returns just as quick when we take it away. So we can see it on the scope, we can see it on the multimeter, we can see it on the scan tool. So we do have a way to manipulate this thing and change and make sure that our sensor is reacting. Now, if you can find the information that tells you how fast it has to react, great, but that's not always shared. Sometimes code set criteria will tell you how long it has to, or how fast it has to change, but that's not something that's always shared with us. All right, let's do some heater circuit testing quickly. So what I'm going to do is we'll start off taking an amperage reading. So I have an amp clamp, we're just going to hook it up to the meter. And we'll hook one up to the scope. Just take a look at what this thing is pulling. Now this sensor's already warm, so we're not going to see anything crazy, I don't think, in terms of amperage. But we should see it start off by ramping up and then slowing down. All right, so our heater's coming in on pin 5. Power is, so I'm going to grab that one. Ooh, I don't think I'm getting 2 amp clamps around here. Alright, we'll see how that goes with just the meter. Actually, let's go like this. I should be able to see. All an amp clamp is converting voltage. I should be able to see that on here. Oops. Okay, let's see what happens. I think we're good. Let's get these extra leads out of the way. Okay, let's take a look at what we're doing for current on our heater. Oops. Keep going the wrong way. So it's doing something. Let's pause it. And we should see pulse width modulation. And this is what our meter looks like for this. So if we get this guy out of here, and let's hook up the Pico one that we can actually just put it into amperage, and I'll show you guys. It's just a little bit easier. Plus there's no math involved. That doesn't look right. Definitely in pin 5, right? Oh. There we go. So we're drawing what, at peak 2.5. So we're within what we need to be. Now, what I want to show you is if you don't have an amp clamp, we're able to make sure that this heater works. So what I'm going to do is we're going to verify that this heater works with a load. We're going to use the test light to simulate the heater. And this is just a real quick test that you can do, but know that if you have the key on and you separate out the circuit like I just did, you are going to run into the vehicle not liking that. Basically, the computer's going to say, hey, I have an open circuit, I'm going to shut it down instead of running into potential issues. So what I'm going to do is I'm going to take and substitute the load of the heater with a test light. So I'm going to take the connector, unplug it, right here, unplug it, and on the connector side I'm going to run one jumper wire into here and one jumper wire into heater control, put the test light across it on the connector side, on the PCM side, and we should see the heater kick in. So I'm pin 5. And you could also take and go on the heater side and measure the resistance across the heater, and you should have a couple ohms. Usually it shouldn't be a short circuit and it shouldn't be open. And then we want to go heater control pin 3. So pin 5 and heater control pin 3. Just make sure that's right. Okay. So we'll go like that. We'll get that out of the way. So again, you can see that I'm not sticking the test light right into the connector. We don't want to spread those terminals out. So we'll hook up I just have another set of jumper leads that I'm hooking to this just so we can get the test light out from underneath there. And what I'm going to do is I'm going to turn the key on. Let's take a look at voltage while this is doing this on the heater control. Oops. Let's go, because I'm going to show you guys what this thing does. It's kind of cool to be able to see what this thing's doing. So we'll just go battery ground on one side, and I'm just going to hook into the control of this thing. So pin 3 will hook into there. And in an open circuit, and then actually let's just go ground across this thing right now. So right now, because we're an open circuit, we should read 12 volts. I have the pins backwards. Let's switch them around so we can actually see it. We should read battery voltage because again, we're testing open circuit voltage. All we're doing is we're measuring the difference between, oh no, we're measuring the difference between this point and this point right now. So we should be reading battery voltage, which we are. But with an open circuit, you'll see that I don't get the heater to control because the PCM has flagged it. So it started to try a little bit of pulse width and then did nothing. So right now, if you have an open heater circuit and you've coded, watch what happens when I hook up our test light across this. So now what we're going to do is we're going to close the circuit with a load. So if we can get a close-up here. Now, nothing happens, but look at the lab scope. And did you hear the engine note change? Suddenly we went to control of the heater and now our test light's flashing. Okay, I'm going to unhook it. The computer's going to look for it. And then it goes back into turning the heater off. As soon as I plug this guy back in or hook this back up, it takes a few seconds for the computer to recognize it's plugged in. And then once it does, it says, okay, we're good, we have circuit integrity. We'll start pulsing the heater. Okay? So just remember that what can happen if you go and start the circuit open, the computer will do a key on open circuit check. And if it fails that key on open circuit check, it's not going to enable the heater. But now if I key cycle, and now if I start this vehicle up with the test light in place, the circuit will be closed. The PCM will be able to understand, yes, I am seeing voltage, I am seeing an intact circuit. I'm going to start the heater right off the bat. And that's what we're going to, oh no, I dropped the key. That's what we're going to see. And right away, we're controlling the heater circuit. Right away, we're flashing the test light. So just keep in mind, if you do any sort of open circuit testing, the PCM might take a minute to re-enable that circuit, because what it's trying to do at this point, oh, my test light got disconnected. What it's trying to do at this point is it's trying to make sure that it doesn't blow its brains out, right? If we have a short to power, short to ground, something causing excessive amperage draw in that heater circuit, it's potential that the ground side control driver inside of the PCM could overheat and fail. So the PCM is very intelligent and it's looking for something specified in the circuit, whatever it is. A test light in this case works because we're only drawing like what, 1/4 of an amp or so, but it's enough that it sends the path to ground. It completes the circuit and we're able to light that thing up, okay? Open circuit testing, be careful because you may not get full control on a smart vehicle. All right. I don't even know if I'm pronouncing right. Nernst, it's just, I don't know. It's a hard word for me to say. Jeremy, the 2013 Dart 1.4 multi-air engine and 2-liter EcoBoost in the 14 Fusion are the two that are in the shop today. Is there anything else that I'm missing here, guys? I know there's a lot more information to cover, you know, equivalence ratio and all this other stuff that I want to cover in future classes. Today, it was a basic, let's look at some heater circuit diag, let's look at some sensor output type of stuff, some tricks that we can throw at these things, because in all of my time looking through the Ford information, through the OBD2 resources, through playing around with the vehicle, the test was never laid out to take the pumping current signal to the ground reference signal and see that movement, that motion in there. That was never laid out in that test. Chrysler actually lays it out in a test in Mitchell service information. They actually had it in there. That's where the idea came from, and it's something that we're able to don't read comments mid-thought, because then you see something from Glenn about how amazing my beard is apparently coming in. Thanks a lot. Completely derailed my train of thought. Beard wet fluid film. So I guess, as with everything that we always suggest, test, don't guess. Have an idea of what you're going to look for. You need to see some sort of voltage values on those pumping circuits. Your 2 pins that go across that Nernst cell should be about 450 millivolts. It should change a little bit if you feed it rich or feed it lean. The pumping current voltage might change a little bit. Realistically, we'll never be able to take that and correlate that directly to an air-fuel ratio because, again, that's happening inside of the PCM. But it gives us a pretty good idea of what we're looking at and a pretty good way to test a sensor that can be daunting for some. So, no, we're not starting anything on fire, although this thing does have a weird transmission issue that I got to look at yet. But let's take a quick look at the t-shirt giveaway. So, like we've been doing the last few months, new t-shirt, exclusive, you have to earn it, you cannot buy it, diagnose before you triagnose, right? These are exclusive, you cannot buy these. There's, been doing this since what, February I think we came out with the shirts, so there's like, what, 15 people out there with these right now? So if you want to join the exclusive T-shirt club, you got to answer this question correctly. And you have to be one of the first 5 to send me out the email. So let's bring it up. 2 technicians are discussing heater circuit diagram and air fuel ratio sensor. Technician A says to verify power and ground to the sensor heater using a test light or something with a slight load that's always less than the actual heater circuit or the actual heater's load. Technician B says to hook the sensor up, the heater circuit of the sensor up to battery positive and negative for about 30 seconds and make sure that that sensor gets hot. If it gets hot, it must be good. So who is correct, and give me the why as well. Tech A, Tech B, both technicians, or neither technician. So first 5 people to send me out an email with the correct answer will win one of the exclusive Diagnose Before You Triagnose t-shirts. All right. I think that's going to cover it for today. I wanted to try to get this done in under an hour for you guys, but there's just a ton of information. I wanted to show you guys everything from a test light voltmeter point of view, because I understand not everybody has the expensive equipment. What's nice is most of the testing that I did today you could do with a single channel scope. So get yourself like the little U scope from AES Wave. You know, that's a great tool to get you in the door of scoping, and then you can look at things in real time. The meter is going to average, so we're looking at pulse width modulation for the heater control. That meter is going to average that. We want to look at it on a scope to get an accurate reading. You can get an idea, but you can't get accurate with the meter because it's not fast enough. It wasn't meant for that. It's a great tool and it's a quick test, but once you get used to using a scope, you rarely use a meter for anything else because you realize the scope can do just about everything you want to do. One other thing I forgot to mention. One other thing. If we look at the wiring diagram, because our pumping current circuits, both pin 1 and pin 2 on here, generally speaking, we're going to see them at or roughly at the exact same voltage on both of them, okay? The problem with 2 circuits coming in at the exact same voltage is you can think right off the bat that they're good, right? Yeah, they both come out with 2.2 volts or whatever it might be. The problem with that is what if those circuits are shorted together? Okay? One of those circuits is going through a trim resistor, and the PCM expects it to be different. It expects the current on that circuit to be different. So what if those 2 circuits are shorted together? We're going to end up with a code. So what you want to do is just a really quick check. I'm not a fan of resistance checks or resistance testing, but I guess this would be a good quick test. You could unplug the PCM and you could verify that the circuits aren't shorted together. What I want to do here is we're just going to do a quick resistance check across pin 1 and pin 2. So either side of the pumping current. Make sure that we're not doing anything weird here. Get the scope out of the way, got 7,000 leads all over the place. Get this guy out of the way. All right, so we're gonna go pin 1 to pin 2. And all we're doing right now is we're looking for continuity. We're making sure that these 2 are not connected, because if they are, we have an issue, okay? So we're looking for, right now it's showing OL. If I start up if I turn the key on, I think they'll read different. And just making sure my pins are correct before I put any power to the PCM. Okay, we're good. Yeah, so I saw 30,000 for a second there when I turned this on, but really all we're looking for is no continuity between the 2 circuits. That's what we need to see, because if we showed half an ohm or whatever between these 2 pins, if we showed it between current control, either side of our pump here, if we showed it between there, we would have a potential shorted circuit, and we run into some pretty odd issues with that thing. All right, so hopefully you guys are blowing up my email inbox right now with t-shirt answers. Yes, Oz, you're right. Please drop a big thumbs up for this. I really appreciate that. All right. Yeah, there was a lot of back to the scope again, you pusher. Sorry, Eddie. It's such a fantastic tool to be able to see stuff over time. Scoping multimeter, graphing multimeter would probably do similar, it's just not as fast. It's just looking at things on a multimeter is just slow. It's good for looking at something that's consistent. Are we looking for power? Are we looking for ground? Are we looking for resistance? Are we looking for that kind of thing? Great for a multimeter, it's fast. The scope though, seeing things over time, it's just so much more beneficial. Anything else? How do you hook a scope to a rubber band, Terry? I don't follow. That's all right, I'm glad you were able to make it at the end here, Terry. I appreciate everybody coming in and viewing this today. I really appreciate everybody being here. It looks like there was a lot of good chat. There's a lot to talk about today. There's a lot to cover with these sensors, which is crazy to me, right? Because it's one sensor with 6 wires. How hard can it be? But the information is just very vague. There's not a lot of information out there. There's a lot of questions. There's always been a lot of questions around the wideband air-fuel ratio sensor. So I hope in the last hour and a half I've answered those questions adequately enough that you guys can go out and you can take these things on yourself. If you get an air-fuel ratio sensor code, please, 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 please don't just unscrew that sensor, put a new one in and hope for the best, okay? Test it. Remember to reset your computer's memory, keep a live memory on Ford or whatever it might be on any other vehicle. Reset those learned values because they can lead you astray. Make sure that there's no related TSBs or reflashes or anything like that because we see that as well with air-fuel ratio sensors, okay? So I really appreciate everybody watching and commenting and hanging out. If you really enjoyed this, please give us a thumbs up. If you aren't already, please become a subscriber. That way you get notified when these new classes come out. And then I think we'll be seeing you guys the week after Independence Day. So yes, July 11th is when we're going to be live next, and we're going to either be covering air-fuel ratio sensors on Asian vehicles or European vehicles. Haven't decided which one to throw in there first yet. Still working on that. It's going to depend on getting vehicles in here to show you guys. Unfortunately, I didn't have any bad domestic vehicles to show you, but I do have an example for a bad air-fuel ratio sensor on an Asian vehicle as well as a European, fingers crossed on that one, that it's air-fuel ratio related. But we'll have some broken examples in the next 2 classes, so I really appreciate you watching again. Let's throw that question up once more. We have somebody asking for my email. Email's right there at the bottom of the screen. Send me out that email with your with the answer. What setting did I use on the meter? For which part? Right now I'm on ohms for resistance for checking continuity between the 2 circuits. Before I was just on DC volts, just watching DC voltage. So most meters should be able to do those 2 things pretty easily. Again, there's my email up on the screen along with the question. Please make sure to get that answer out quickly because I'm sure it's filling up my inbox. So, all right, I'm going to get out of here, guys. Thank you so much for watching, and we'll see you again next time in the NGK Tech Garage. Thank you. Happy wrenching.